Hello, my name is Leo. Today we are going to talk about cryptographic algorithms. We are going to give you examples of both traditional and modern cryptographic systems. They mainly differ in their keys and complexity. Traditional cryptography is the simpler one, which uses only one key, a secret key, which is known only by sender and receiver. This is why traditional crypto systems are symmetric. The more complex crypto systems weren't needed because in the history people had in most cases opportunity to meet each other and then exchange their secret key. However, today people exchange messages with anyone located anywhere in the world, so this way would not be so efficient. There are in modern cryptography also symmetric keys, but they are not so widespread. There are more complex crypto systems where more keys are used, public, which is published in public, and private key, which is only known by sender and receiver. This is why they are asymmetric. In encryption and decryption processes use different rather than the same key. First, we are going to talk about traditional cryptographic algorithms. There are more types of traditional crypto systems, and we are going to give two basic types, monoalphabetic and polyalphabetic. Let's take an example of monoalphabetic crypto system. One of the first crypto systems was so-called Caesar cipher. It was cipher which works on the principle of letter shifting. We take a message and each letter in the message shifts for predetermined number of places, which is determined as the key. Here we have example of message word. Our key, so shift, is set to 3, which is the most common key for Caesar cipher. For this we'll need the table of letters and their positions in alphabet. We have here. First step here is to find position of every letter in the message, which you can see in this table. Next, do the shift of all of the letters for the determined shift, it's 3 here. Finally, construct the table with the new positions, which are the previous ones increased by 3, and write them next to them, their matching letters. This is how Caesar cipher works. Let's talk about polyalphabetic crypto systems. An example of more complex crypto algorithm is Vigenère crypto systems. Here we have example of a sentence as message, it is sunny, and word today as a key. For the encryption process using Vigenère cipher is used a table like this one. Let's combine letters in the next way to get cipher. In the table you can see each letter from original sentence is paired with a letter from keyword in the way that the letters from the keyword are written below the letters of the sentence to the end of the sentence. In the end, two letters in the same column are considered as pairs of letters, and thus in that particular combination they give a new letter determined by the table. If we have, for example, letters I and T, which is here first pair of letters, then we look at the column I and row T, or column T and row I, to find the letter on the place where the column and the cross each other, letter B. Let's go to the modern cryptographic algorithms. We are going to observe two basic examples of modern cryptographic algorithms commonly used. Just to mention, in the examples we are going to use names which are usually used in cryptography. Alice for sender and Bob for receiver. There will be also man in the middle, who is the person Alice and Bob wouldn't like to get know their private secret keys, called Eve, the eavesdropper, listener in, the man in the middle who always wants to get the decrypted information for herself. The first example we have here of a modern algorithm is Diffie-Hellman key exchange. Firstly, Alice and Bob have to agree on two prime numbers, prime number p and prime modulus q. Take p is equal to 7 and q 13. These are published publicly so that anyone like Eve and also Alice and Bob can get them. Next, Alice chooses a private number, say a is equal to 14, and then does modular exponentiation arithmetic of p to the power of a modulo q, which is here 7 to the power of 14 modulo 13 equal to 10, as we can see. We can calculate this using computer. This gotten number 10 is sent publicly so that anyone, including Eve and Bob, gets them. Then Bob chooses his private number, say B is equal to 17, and then does modular exponentiation of b to the power of b modulo q, which is here 7 to the power of 17 modulo 13 equal to 11. This 11 is sent publicly so that anyone including Eve and Alice can get them. Finally came the most interesting part. First, Alice takes Bob's public number, 11, and raises it to the power of her own private number, 14, and does the modular arithmetic with q, equal to 13. So we have here this arithmetic, which is 11 to the power of 14 modulo 13 equal to 4. Bob does analogously the same thing. He takes Alice's public number, 10, and raises it to the power of his own private number, b is 17, and does the modular arithmetic with q equal to 13, which is here 10 to the power of 17 modulo 13 is 4. So Alice and Bob have gotten the same number. Why is this so? The answer is they've done actually the same calculations, but in an not so obvious way. Let's prove that. The Bob's public number, 11, has been gotten as 7 to the power of 17 modulo 13. Therefore, 11 to the power of 14 modulo 13 is congruent to 7 to the power of 17, to all of that to the power of 14 and this modulo 13. Furthermore, the Alice's public number 10 has been gotten as 7 to the power of 14, all of the and that modulo 13. Therefore, 7 to the power of 14, all of that to the power of 17, and this modulo 13 is congruent to the first expression we've got. Since some a, number a, raised to some other number b, and all of that to number c, is equal to a to the power of c and all of that to the power of b, then also the a to the power of b and all of that to the power of c modulo x, some number x, is equal to a to the power of c to the power of b modulo x, meaning modulo of number raised to power of b and then to power of c is equal to modulo of number raised to power of c and then to power of b. These powers are actually private numbers, private keys, and the public numbers are public keys. To conclude, only Alice and Bob would be able to decrypt data using their private keys, while encrypted data can be seen by anyone such as Eve, but she cannot decrypt, cannot get the original plaintext she's interested in. Diffie-Hellman key exchange algorithm is so great because of applying of so-called discrete algorithm problem, which enables just this issue that Eve and any other man in the middle cannot decrypt ciphertext without knowing the key. From the example that 10 to the power of 17 modulo 13 is equal to 4, where 10 and 13 are numbers publicly known, but if we only know them, and even if we try using Diffie-Hellman algorithm to decrypt cipher, we'd have 10 to some unknown number x modulo 13, which can be equal to any of the 13 possible remainders from 0 to 12, which can be gotten when dividing by 13. However, only Alice and Bob can get the result using their private keys. So this is why these are asymmetric cryptosystems. Public key is the key Bob uses to encrypt data, while private keys are used both by Alice and Bob in decryption process. The next is RSA algorithm. Here we're going to present an example of RSA encryption. We are going to use much smaller numbers P1 and P2 than they are normally, as hundreds digits long numbers. First, Alice randomly generates two prime numbers, P1 and P2, and multiplies them to get number n, which is product of P1 times P2. This number is then published. Let's take that P1 is 47 and P2 is 37, which we get that n is 47 times 37 is 1739. This n is published for anyone to see. The next step is that Alice needs to find the prime factorization of the big composite number she's gotten by using Euler's Tauschen function called phi function. Phi function of some number x is a number of numbers which have at least one common divisor with x except 1. For example, phi of 6 is equal to 2 since only 1 and 5 are numbers smaller than the given number, number 6, which do not share any common divisor with 6. Phi function has property which is that phi of some number p is p minus 1, where p is prime number. Since every prime number has no numbers it is divisible by except by 1 and by itself. For example, phi of 5 is equal to 4, 5 minus 1, and has also multiplicative property. Using these two properties, the next can be derived. So phi of number n is phi of n, which is product of p1 times p2. This phi of p1 times p2 can be, thanks to multiplicative property, separated into phi of p1 times phi of p2. And then phi of p1 is p1 minus 1, phi of p2 is p2 minus 1, and we get that phi of n in this example is 46 times 36, which is 1656. Next, Alice chooses a small odd number which must not have any common divisor with phi of n. Let's say it's e equal to 5. Then calculate number d. Number d is here so-called trapdoor for this encryption process. The only person who has access to it is Alice, sender, and therefore no one else can decrypt this cipher except Alice. This is the application of one-way function, the basic concept of functioning of all asymmetric cryptosystems, although here is introduced additional parameter which makes the decryption process for man in the middle even more difficult, the trapdoor number d. Now use Euler's theorem expressed for d. Here we have expression. For this we already have phi of n and the number e, and k is a number coprime to n, and if possible such a number so that we get d as an integer, such as k equal to 4 in the example. And now we calculate d equal to 1325. And when this calculation is over, Alice sends numbers n and e, which together make public key. So this key is received by both Eve and Bob, and by both Eve and Bob, as we can see. Bob uses n and e numbers to encrypt message and get c defined as m to the power of e modulo n, where m is number of Bob chooses. Let's take that m is equal to 73 we have here. Then c is equal to this expression, so it is 73 to the power of 5 modulo 1739, which is 998, which is shared publicly. Alice also gets this c from Bob and calculates c to the power of d modulo n, where she has to use her private key d in order to decrypt ciphertext into plain text form so as to get Bob's m equal to 73. Finally, calculate this using this expression. So this c is 998 to the power of d, which is 1325, modulo 1739, which is n, is equal to 73 and is equal to m. We can see that it is really true that c to the power of d modulo n is equal to m. All in all, RSA algorithm is only one of today's commonly used cryptosystems for securing computer data. It is so great because it requires man in the middle to know prime factorization of a big number n to get exponent d, Alice's private key to decrypt ciphered message. Prime factorization of big numbers is one of the problems for which even today's networks of computers would have to calculate for years or for hundreds of years to find it. Now only a few words about the people creditable for this algorithm. A system equivalent to RSA as algorithm was developed in 1977 by Clifford Cox. By the first three who publicly described their algorithms, this algorithm were Ron Rivest, Adi Shamir, and Leonard Edelman, after whom RSA algorithm got its name, so after the initial letters of their last names. In this video, you've got an insight into cryptographic algorithms. You've learned about the ideas presented as the base of each algorithm. Also, you could have noticed complexity of cryptographic algorithms used today, which is important for making data even more secure. You could see prime numbers and prime factorization play a very important role in modern cryptography, which is simultaneously one of numerous examples how mathematical concepts are efficiently applied in computer science. Thanks for watching and stay with us.